Well, hello everyone. Welcome to our course on differentiable simulation. My name is Stelian Koros. I'm a professor at ETH Zurich, and it is my pleasure to be co-organizing this course with Bernhard Tomaszewski, Miles Mackling, and Niels Thury. As legend has it, Sir Isaac Newton was resting under a tree, just minding his own business, when an apple fell onto his head. This traumatic event led him and many others on a quest to understand the laws that govern the way everything around us moves. An apple falling from the tree, a blade of grass blowing in the wind, the flapping flight of birds and insects, even the perpetual motion of entire galaxies. Fast forward a few hundred years later, and this understanding of the laws of physics is enabling us to create vast virtual worlds that look and feel real. Now, in creating scenes like these, physics-based modeling is a core underlying technology. For the purpose of this course, we assume you are more or less familiar with the basics of forward simulation. And we are here to discuss a new paradigm, differentiable simulation. So what is this exactly? To answer this question, let's take a look at a concrete example. What we have here is a typical simulation environment where we want to model the way a beach ball moves according to the laws of physics. What we need in order to do this is a description of the environment, where is the floor, where are the walls, that sort of thing. A description of the shape, mass distribution, and material characteristics of the beach ball, as well as its initial position and velocity. If we have this information, then we can predict the trajectory this ball will take within the virtual environment. If the simulation is fast enough, we can interactively change the initial velocity or spin of the ball, and we can immediately visualize the way its motion trajectory will change as a consequence. This is called the forward problem. Predict as accurately as possible how a physical system will evolve over time. Now, let's say we want this ball to land at a particular target location. What should its initial velocity and spin be? This is an inverse problem that we can solve computationally thanks to the concept of differentiable simulation. Let's take a closer look at how this works. Forward simulation, as I already mentioned, takes as input a description of the mechanical system we're modeling, as well as a set of parameters, we're going to call these P, which for this particular problem would represent the initial velocity of the ball. Running the simulation gives us a motion trajectory for this mechanical system, and we're going to call this x of p. For an inverse problem, we also need a goal. For example, we might want the ball to land in this cup. We can describe this goal mathematically through an objective that measures the distance between the target and the position of the ball at the end of the motion trajectory. If we want to use a gradient-based method to find the input parameters that minimize this objective, we will need a gradient, which we can compute easily using the chain rule. Now, what we see here in the expression we have for the gradient of the objective is the Jacobian dx dp. What dx dp tells us is how the motion trajectory computed through simulation changes as we vary the input parameters. So there we have it. A differentiable simulation computes not only a prediction of how a physical system will evolve through time, but also the derivatives of this prediction with respect to certain input parameters. How do we compute these derivatives? Well, let's take a look.
Hello, everybody. My name is Bernhard Tomaszewski, and in this part of the course, we'll be taking a look at the basics of differentiable simulation. Now, at the very outset, we could talk about the question of what that actually is, differentiable simulation. And maybe in the most generic setting, differentiable simulation answers the question of how a change in parameters of a given computational model affects the outcome of that simulation model. So that's the question we want to answer, and we're going to take steps towards answering these questions in the following. We'll be looking at a simple example here, simulating the static equilibrium of a 2D elastic bar that's fixed at one end, say to a wall, and that's subjected to a set of forces, external forces, which we call Fx. We'll use the undeformed state of that elastic bar as the parameters, which we call P, and we'll assume that, well, the whole system has n nodes, and because we're in 2D, we have 2n degrees of freedom. Now, for a given choice of rest state, for a given choice of parameters, P, and given external forces, we can compute the corresponding equilibrium state, the deformed state, X, just by using simulation. Now, it's already clear that when we change the parameters, that means when we use a different rest shape, then we'll generally observe a different equilibrium state. But the question is, what exactly is this map between parameters and equilibrium state? And how can we compute the derivative of that map, that is, the derivative of the simulation? So to that end, we'll start by first making things a little bit more concrete. We'll talk about how to compute the internal forces. And here, the goal is really not to be very sophisticated, but more to just have a simple model that'll be sufficiently meaningful for us to see how differentiable simulation works. And for that reason, we're using something simple, generalized springs, where for each edge in this mesh here, we would set up an energy term that penalizes the difference between the current length, Lij, compared to the initial length, capital Lij. And then from that, we get the elastic forces that act on the nodes of the springs just by computing the negative gradient of that potential energy. And when we do that for all the edges in the mesh, and we sum up contributions for in every node, then we can compute the internal forces that act in every node, just as the sum of the spring forces for the adjacent incident edges. So all of that is really not very complicated. It's not sophisticated at all. But the advantage of doing something simple like that is that we're able to compute derivatives if we wanted to do so by hand, first and second order derivatives, which we will need later on. So now that we have that, we can talk about what it actually means to do simulation. We're looking at a static equilibrium problem here, which just means we are looking for a single configuration, a deformed state X, that satisfies the equilibrium conditions. Now, what are those equilibrium conditions precisely? Well, we can say that in order for X to be an equilibrium configuration, the net forces acting in each node have to vanish, which means that the sum of external and internal forces has to be 0 for every node. But that's pretty clear, because if forces were not 0, then we would have a corresponding acceleration in the nodes, and then things would move, which contradicts the assumptions that we're in a static equilibrium configuration. This force condition by itself is necessary, but it is not sufficient to be at a stable equilibrium point. In order for us to be at a stable equilibrium, which means that we can perturb the system slightly and it'll go back to the initial equilibrium configuration, we need a somewhat stronger assumption, stronger condition, which is simply that the system must be a stable equilibrium point. It must be the minimizer of the potential energy, where the potential energy is the sum of internal elastic energy and external energy. Now, in this case, the potential energy is simply the sum of internal and external energy. And we've seen the expression for internal energy before. External energy here could be just gravity, or it could be the work done by the external forces. Now, we have a map between parameters, the rest state in our case, P, and the corresponding equilibrium state, X. For any choice of P, any reasonable choice, let's say we don't want inversion, we don't want the mesh to collapse, but for any reasonable choice, we can apply simulation and obtain the corresponding equilibrium state, X. And for that reason, because we can do that for an arbitrary choice of P, we can also think of x now being a function of p, and that function is actually simulation. Simulation, in turn, we've seen on the previous slide, is an energy minimization problem. It's a minimization problem in general. So if we were now going to ask the question, how does the equilibrium how does the equilibrium state x of p change as a function of the parameters p? It very much looks like we want to take the derivative of this process, simulation. But what does that actually mean? Can we take the derivative of the simulation directly? It sounds like we would be taking the derivative of a minimization process, and that sounds rather complicated. What we would have to do there is we would have to take the derivative of Newton's method if we're using that for minimization. And there are many questions coming in here. One of them is like, how many iterations are we going to use? Because in order to take the derivatives of all the computations that we're doing in this process, we have to know how many times we're applying it. And in general, that is not known in advance. Inside every Newton iteration, we'd be solving a linear system. And again, we might be using an iterative method here. And then the question, how many iterations do we need? That's again, difficult to answer. And there are many other reasons for why we don't really want to take the derivative of the minimization process here. But we can do something else. And to that end, let's look again at the conditions that we have, or the assumptions. First of all, we already said that x, the equilibrium state, is a function of the parameters p, and we write x is equal to x of p. And we also know that for any pair x and p that corresponds to an equilibrium state, the internal and external forces must sum to 0 in every node. So the question now, what happens when we change parameters, when we perturb them slightly, is, well, for a given change in the parameters, delta p, we will observe a change in equilibrium state delta x. We don't know yet what that delta x is going to be precisely a priori, but what we do know is that in order for the new state, x plus delta x and p plus delta p to be physically reasonable, the forces at that new state have to be 0 again. Otherwise, it's not an equilibrium configuration. And that expression here, that the forces must remain 0, that's something that must hold true for any parameter change, delta p, that we're applying. So we can actually write this expression in a more general, in a more formal way by saying that the total derivative of the forces with respect to the parameters must be 0 at all times. And that we can split up into the partial derivatives. We see that we have a partial derivative of the forces with respect to the positions x. That's just minus the Hessian of the elastic energy, the force Jacobian, times the partial derivative of equilibrium position with respect to the parameters. And then also we have a third term, that's the partial derivative of the forces with respect to the parameters. So in all of this has to remain 0 when we change parameters, no matter how we change them, in which direction we're going in parameter space. Now, what we see in here now is actually what we're looking for. This expression here, dx dp, that's the simulation derivative. And we're already given it in a analytically closed form sense. Just we have to invert this matrix df dx, the force Jacobian, and then multiply df dp onto it. In practice, of course, we don't want to really invert that matrix here. And we talk about how we can compute dx dp, or at least parts of it, in the following. But the essential idea here is that this is the structure of the problem that we're exploiting in order to compute simulation derivatives. We're not going to take the derivative of the whole minimization process. We just need this expression over here. All right. So this is what we're starting with, what was just derived. This is also called, or often referred to as, sensitivity analysis. Dx dp is called the sensitivity matrix. And the underlying theory for that, the mathematical framework, so to say, it's the implicit function theorem. We'll have a look at that in just a minute, because it gives us more insight into what are the conditions for when we can actually compute this. But for now, what I like to mention here is that this is only one way of computing simulation derivatives. And there are many other alternatives. For example, a simple way of computing this expression would be through finite difference approximations. And in some cases, this might even be reasonable. If there are very few parameters, let's say, then we can compute this derivative with a few simulations only, and that might make sense depending on the application. If we go into higher number of parameters, however, then this quickly becomes infeasible because the numbers of simulations that we have to run grows very rapidly, and then it becomes computationally intractable, or just at the very least not attractive anymore. An alternative here would be to use a learned model, for example, using a deep neural network for the simulation. And then if we have this deep neural network, we have that in closed form, and we can take the derivative of it. So that would be an alternative. Of course, we first would have to train it on a number of simulations. And then the question is, how well does that generalize to different types of simulations? But nevertheless, this is an alternative that is also explored in previous and concurrent work, and it's certainly worth consideration. We'll actually talk about this in the later part of this course. And somewhat related to that is auto differentiation, which we'll also hear more about later in this course. So for now, let's have a look at this implicit function theory, in which asserts when the derivative of the simulation actually exists and what are uniqueness conditions. So for that purpose, we'll assume that we have a function. It's it's a generic one, no assumptions made, except for that it maps from a parameter space of dimension n plus p, which would be degrees of freedom plus number of parameters, and it should be continuously differentiable. In our case, that function f would actually be the total forces acting on all of the nodes. So if for a given reference configuration, it doesn't have to be really the rest state, but just some point around which we have already computed the equilibrium configuration, let's call that x0, and for a corresponding set of parameters p0, such that that function f is actually evaluates to 0, which means that we are at static equilibrium, at least the first order conditions for stable static equilibrium are satisfied. And if additionally df dx is invertible, well, then there exists a unique continuously differentiable function x, such that f of x of p is equal to 0 for all p in a certain neighborhood and around p. Now, the important aspects in this definition are really that, well, this has to be 0, f has to evaluate to 0. Otherwise, if it is not 0, computing the derivative here is not very meaningful from a physical point of view, because then we would be asking the system to stay at a constant off-balance force, and that really doesn't make sense for us. The more important criterion here or condition is that df dx has to be invertible, which also includes that df dx has to be a square matrix, of course, and it must not be singular. But if these conditions are satisfied, then we know that we can compute the map itself and its derivative, and it's going to be valid and unique, at least in a certain neighborhood around the point which we're currently at. Now, that is rather satisfying from a theoretical point of view. Now, let's have a look at a few computational aspects here. So the simulation derivative dx dp, one thing that's important to note is that it's a dense matrix. It has dimensions, the number of degrees of freedom, of course, times the number of parameters. So this is not a square matrix in general, but it's in pretty much all cases, we can assume that it's a dense matrix, which of course has implications from a computational point of view. Well, we can compute that matrix by solving NP linear systems instead of just inverting the matrix df dx directly, which is in general much more approachable computationally than computing directly the inverse of the matrix. I guess that goes without saying, really. And then Another point would be that it provides a first order prediction for the change in equilibrium state incurred by a given change in parameters. Well, I'm emphasizing this first order here because, of course, it's just an approximation of the new state. And what we've seen on the previous slide is that in order to apply the implicit function theorem, we really need the system to be in static or later also dynamic equilibrium at all times. And in most cases, the first order prediction is not sufficient. We really have to reproject the system onto the manifold defined by forced equilibrium, which means that we, in most cases, have to do a full nonlinear simulation to find a new point. Now, in most cases, we're actually not interested in computing all of this matrix, dxdp. We might not only be interested in its action onto a certain direction in parameter space. Let's call that direction in parameter space delta p. So if we're given that direction, if delta p is known, then we can compute the corresponding delta x in this way over here. Of course, we would just say the first order we have dxdp times delta p. But if we plug in the expression that we had on the previous slide for dxdp, then we arrive at this expression over here, and that actually can be used to simplify things a bit. So instead of computing the entire matrix, dx to the power of -1, the inverse here, we would solve the system, we would solve for delta x in 2 steps. First, we introduce a vector that we call b, which is simply this part of the equation over here. Well, that's very simple. But then we're left with this expression here times b is equal to delta x. And that we can actually convert into just a single linear system where we solve for delta x with a given right-hand side b and our given forced Jacobian df dx. So of course, that is much more efficient than first computing delta x and then multiplying delta p onto it. In general, if we have more than one parameter for sure. So this requires only one linear solve instead of the number of parameters, linear solves, and it's in general much faster. So now we're able to compute a delta x for a given delta p. But what are we actually doing with this? What do we do with this simulation derivative? So let's look at one example here, which is solving an inverse statics problem, where we're really asking, we're given a target shape, which you see in blue here. And the question is, what are the parameters of the system P? What is the rest shape such that when we apply simulation to that set of parameters, we'll observe a simulation result that is as close as possible to this target shape here. So that's the inverse problem. And we'll use differentiable simulation to solve this inverse problem. The first thing that we have to do here is we have to be able to quantify the distance between our current simulation result and the target shape. And we do that with a so-called objective function or a metric function, which measures the distance to the target. In this case, it's just an L2 norm over the pointwise distance between our current configuration and the target configuration, which we call X target. And then we sum over all of that and look at the difference vector and take the norm squared. That's probably the simplest way of expressing such a target metric. What we also have here is a regularizer R that only depends on P and not on X directly. That we might need in order to prevent distortions, too large distortions in the mesh, or perhaps we also have a null space in this problem, meaning that several configurations or maybe a whole subspace of parameters will lead to equilibrium shapes that are equivalent from the point of view of this distance metric over here. So for that reason, we're introducing this regularizer P as well. Now, once we have that, the target, distance to the target, this metric, we can actually solve the inverse problem simply by solving a minimization problem, because we already have the derivative of X with respect to P We just minimize over the parameters and plug in the x as a function of p directly into this objective function t. Now, if we want to minimize, solve this minimization problem, we must at least be able to compute its gradient. And that gradient here, we of course need the total derivative of the objective with respect to the parameters p, not just a partial. And that total derivative, we've seen this before, we can split that up into the partial contribution. Once just the gradient of t with respect to x, in our case, that's very simple because the objective is quadratic in x, times the simulation derivative dx dp. And then we also have the direct partial derivatives of the objective function t with respect to p, which in our case would just be the derivative of the regularizer. Now, just for concreteness, let's split this up again. Let's plug in the expression for dx dp. And what we'll end up with is this expression over here, nothing too dramatic for now. Let's also apply this transposition operator to the two factors inside the parentheses, such that we end up with this expression over here. And again, this exercise we're only doing because we don't want to compute the entire matrix dx dp if we can avoid it. We only want to compute its action onto this gradient of the objective in equilibrium space. And now, similar to what we've seen before, we can apply this little trick here by just evaluating this term that we've highlighted here first, and then using it to compute the total derivative with the remaining expressions over here, the remaining terms. And this is how we would do this. We would first solve a linear system corresponding to that highlighted term here for an unknown vector. This time we call it g. Once we computed that g with a linear solve, we can just plug it into this expression over here to obtain the total derivative of the objective function with respect to p. Now that's great. We can compute the gradient of the objective function. And with that gradient, we can try to solve the minimization problem using some algorithm, a minimization algorithm that uses gradient information, the one that we like best. Probably the simplest one that we can think of is gradient descent, which essentially means that in each iteration, we compute an update to the parameters, an update to the rest state, just by walking along the negative gradient of the objective function. We would scale that gradient by some factor alpha, and that factor alpha is chosen such as to, well, get good progress, but not overshooting. So simply said, but this is actually something that's not so easy. In general, we would probably want to apply line search in each iteration to find a parameter, a step size that works. But once we have found that update delta p, we apply it to our current parameters, and then we also use the new parameters to update our equilibrium state x by setting it just to x plus delta x. But here we're saying delta x as a function of p because, as we said before, we could compute a first order approximation to delta x using the simulation derivative dx dp. That's possible, but in general, it's not sufficient to really ensure that we're at equilibrium again at the new configuration. So we might actually have to do a simulation step to really arrive at forced equilibrium again. And so these two things, the fact that we have to first find the right step size and that we have to do simulation, actually make gradient descent rather expensive per step. So the question is this really a method that is going to be reasonable in the general setting? And the answer to that is, in general, no. So let's look at an example here for how gradient descent would work. It's again this simple didactic example that we've been looking at before, just that now we're really doing simulation. And that might not be immediately visible here, but this is now a 3D simulation with a slightly larger mesh. But the idea remains the same. We're solving a static equilibrium problem. Everywhere in every node, we have an applied force, it's just gravity. At the left-hand side, we're fixing the simulation mesh. Initially, if we start with a straight horizontal bar, then we're observing a deformed configuration that looks like this. And now we can take steps of gradient descent, and hopefully we're getting closer to our target shape here. We want the bar to be actually a straight horizontal configuration in its deformed state. So that's what we're trying to do. So we take one step of gradient descent, and well, it does something, as you can see here. Somehow the nodes here, they moved up and down. And also, if we go a little back and forth, we observe that, yes, indeed, the deformed state got sort of closer to horizontal, but it's still very far away from it. You can also tell that the objective here, well, it's relatively small. It's 6.6 times 10 to the minus 1, but it's really not very different from the initial target objective value. So if we take another step, another 9 steps actually, after 10 iterations of gradient descent, well, we can see a trend here. The bar straightens out somewhat, but the rest state also bulges out. Not sure if this is really beautiful, but what we have to do here also, I didn't mention that yet, is that we apply a regularizer that prevents too large deformations in the individual elements. If we didn't have that, then these strong concentrations here of deformations would be even more pronounced, and eventually they would lead to those triangles or tetrahedra in 3D to become squashed, and that would be a problem for simulation. So we have a term, the regularizer here, that asks for these deformations to be as small as possible. So if we go on after 100 iterations, that process essentially continues. We're getting more concentrated deformations around the point where we're attaching the bar, and the bar straightens out. But even after 1,000 iterations, no, we can see the trend again, but we're still rather far away from the state where we want to be. And that's also reflected in the objective value here, which is 1.3 times 10 to the minus 1. It's like 6 times smaller, approximately, maybe 5 only, but it's still very far away from the optimal. So long story short is, if we're just using gradient descent, then, well, we have to set ourselves up for a large number of iterations that are required to solve even such a simple problem. And then each iteration will require a full simulation and, well, computing the simulation derivative. And those costs, they will add up, and it makes the whole process with gradient descent very slow. So what can we do to accelerate solving inverse problems like this with using the simulation derivative? One of them would be to use quasi-methods, quasi-Newton methods for acceleration, such as BFGS. That would arguably be the best known method among those. You can use like a limited size, window size BFGS, where essentially we're just keeping track of the last n states, the gradients, and the difference in configurations. And then from that, BFGS constructs an approximation of the Hessian of that minimization problem, and uses that information to make faster progress towards the solution. Now, if we're doing that here, again, LBFGS, starting from the initial state, a straight elastic bar and its corresponding equilibrium state, we take one step of LBFGS, and we can see that it looks, after 5 steps, it already looks, it looks sort of similar to what we've seen with gradient descent, perhaps after 10 or 100 iterations. So that seems to be a little better already. And then if we take another 15 steps, yes, that also makes progress, maybe as good as like after almost certainly several hundred gradient descent iterations. And then after 50 iterations, we really start to get close to the optimum solution. And after 100, we're fairly close. We have like reduced the objective value by at least 1 order of magnitude, 30 times perhaps. And that starts to look good. But Again, each iteration of LBFGS also requires simulation, maybe several simulation steps if we have to do line search and cut the step size in the loop. So also that, if you're using like 100 iterations, that's not for free, certainly. So yet another option that we have, if we want to have further acceleration, would be to use higher order information, not just derivatives, but at least some part of the real Hessian information of that problem. So in order to get an idea of how that could work, let's look again at the gradient first of that minimization problem. The total derivative of it, we've already had that. It involves the simulation derivative itself, the gradient partial derivative of the objective in equilibrium space and in parameter space. Now, higher order derivative would mean in this case a second order derivative of this objective function t. And if we just compute that and do like the math, the calculus, so to say, directly, that's the expression that we would be ending up with. That is certainly a little bit unwieldy to look at, but we can identify a few terms here that do make sense. For example, that would be just the Hessian of the regularizer with respect to the parameters. Here we have the Hessian of the objective function with respect to the equilibrium states, sandwiched in between the simulation derivative and its transpose. And then we have mixed derivatives also here. And finally, we have the second derivative of the simulation outcome with respect to the parameters. And now this last term, actually, this is very complicated to compute and would take a long time. And it also turns out, through experiments, we've seen that time and time again, that this is actually adding indefiniteness to this Hessian over here. And so for those reasons, it's not really desirable to compute this term here in a general setting. But what we can do is we can just discard it, and we can just take what's left in this Hessian of the objective. And that's actually what is also known as the Gauss-Newton method. It's an approximation of the true Newton method that we would be using when we use the full Hessian. So we can discard this term here, and then instead of using just a gradient, we compute a search direction by solving a linear system with this Hessian approximation, the Gauss-Newton approximation as the matrix, and the current gradient of the objective function as the right-hand side. Now, this works, but the problem is that the Hessian here, well, it's a dense matrix, which already isn't great because solving dense linear systems for a large number of problem variables, of course, that takes a long time. And also computing this Hessian itself, that this time around really requires us to compute the full simulation derivative for all of the parameters. And depending on how many parameters we have, that is really a lot of computation that we're looking at. So if we could avoid this and still use the same information to compute a search direction that hopefully gives us a faster descent and uses second order information, that would be great. And so for that reason, to make progress into a more practical, more tractable formulation, we first rewrite the Gauss-Newton Hessian in a bit more of a symbolic way. It's not really doing anything new here. We just replaced some of these like unwieldy terms by symbols A, B, C. And that also highlights a bit the symmetry of this Hessian here. We have again the sandwich product, and then we have a term B appearing here once a transpose form, and then C that would be the Hessian of the objective function, the regularizer itself. Now, what can be shown actually here, and what we did show in a recent publication and transactions on graphics, is that solving the dense system here that we've seen before is actually equivalent to solving a larger system over here, this one, a larger system that has like involves a larger number of variables, but it's sparse. All of these blocks are actually sparse. You can see that we have a bottom block here that is entirely 0, which sort of reminds us of the system, the saddle point problems that we are facing when we are solving the first order optimality conditions from a standard constraint optimization problem. And indeed, this is also a way of showing the relation between this kind of simulation derivative sensitivity analysis and standard constraint optimization through Lagrange multipliers. There's more information in this publication that I'm listing here on the bottom, but the important point that I would like to make here is that these systems are completely equivalent. When we solve them, the delta P that we're getting out of them is going to be exactly the same. Just that one system here, one of them is small but dense, the other is large but sparse. And in general, for the problems that we're interested in particular for rather large number of parameters, it turns out that solving this large but sparse linear system is asymptotically faster than solving the dense system. This is just one illustration that you see here, which just scales a lot better with increasing number of parameters than solving the dense system. Now, using this method, which we like to call sparse Gauss-Newton, we can apply this to our toy problem from before. And what we see is that even after one iteration, we're already very close to the optimum state, actually closer than LBFGS after more than 100 iterations. And if we take another step, we see that the solution changes slightly, but the objective value is now something like 10 to the power of -6. So we're really close to the optimum value. And then another iteration will get us all the way to -12, which also nicely shows that we're getting even quadratic convergence in this case. All right, so that concludes the part on some of the basic concepts of differentiable simulations. And we'll hear more about some of these aspects in the following parts of this course.
Okay, so we've seen how to formulate differentiable simulation models for static problems, and now we'll turn our attention to dynamics, problems that consider not only force equilibrium, but rather the process of generating entire motion trajectories through simulation. Now, to compute a motion trajectory, we typically have to discretize the time domain. This simply means that we take snapshots of the state of the mechanical system at specific moments in time. And motion trajectories are therefore represented simply as a stacked vector of states. At every discrete moment in time, we must find a configuration of the system that satisfies Newton's second law of motion. This is where we start to have many options in terms of how we can do this. I will not go into too much detail on this. I will just mention that generally speaking, we can categorize time-stepping schemes into explicit and implicit methods, each of which have their own strengths and weaknesses. Now, for explicit time-stepping schemes, what we have to do is begin by evaluating forces at the current configuration of the mechanical system. This allows us to compute the accelerations, which we then integrate forward in time in order to get the configuration of the system at the next time step. For implicit time-stepping schemes, matters are a little bit more complicated. We actually have to run an optimization problem, essentially Newton's method for root finding, in order to find the configuration of the mechanical system at a particular moment in time, such that the implicit relationship between accelerations and forces is satisfied. In what follows, I will mostly focus on the implicit time-stepping setting, but I will note that there are many similarities between explicit time methods, explicit time integration methods, and implicit time integration methods as far as the formulation of differentiable simulation goes. So many of the concepts you can just take and apply more or less the same for explicit time-stepping schemes. All right, so during a forward simulation pass, when we are computing the motion trajectory, we, of course, have to start at the first time step. We compute x1 by finding the solution to Newton's second law of motion. We then proceed on to step 2, where we repeat the process. Of course, now accelerations and forces change, and so on and so forth for every time step. So this is how we compute x of p. Again, p here is the input that's driving our simulation. What we want to compute is dx dp. And x of p may or may not have an analytic form depending on the definition of the mechanical system and the forces acting on it, and whether we're using an implicit or explicit time stepping scheme. Now, given what you've already seen before in terms of sensitivity analysis and so on, it should come as no surprise that if we were to take all these force residuals, basically the relationship between mass times acceleration minus the forces acting on the system, we stack them all into a vector that we call g here, which is a function of x and p. Well, for any p, by construction, we computed x of p such that this vector of f minus ma residuals is always 0. This then allows us to repeat the procedure that we've seen before. We essentially take the total derivative of this residual vector with respect to the parameters that we care about. We set that to 0, expand it using the chain rule, and now we have the typical expression that you've seen before that allows us to compute this Jacobian dx/dp. Now, when dealing with these types of equations, I find it convenient to also look at them in matrix form, because this, I find, allows us to get a very intuitive understanding of what these different terms actually mean. For example, we can look at the individual blocks in the Jacobian dx/dp, and each one of them will tell us how the configuration of the system at a particular moment in time will change with respect to the jth input parameter. And this is exactly the kind of information that we visualize in videos like these, where we wiggle the piece and then we directly estimate how the configuration of every moment in time changes, right? This is basically what's contained in this dx/dp Jacobian. Now here you have to be a little bit careful about the distinction between partial derivatives and total derivatives. This is basically what allows us to compute dx/dp analytically, even though x of p might not have a closed form expression. So now if we take a look at, let's say, the matrix that encodes partial derivatives of g with respect to x, well, every block in this matrix will tell us how the f minus ma residual at time step I will change with respect to the system configuration at time step j. And now for backwards Euler, basically the simplest implicit time stepping scheme, we can write down the force residual for this, or the f minus ma residual for this particular moment in time with a discretized acceleration term. And once we do that, I hope it'll be quite clear that many of the blocks in partial g, partial x will be 0, because at time index k, this physics residual only depends on the state at time index k, k minus 1, and k minus 2. Therefore, it's easy to see that we get this type of sparsity structure for this matrix of partial derivatives. Now, we can analyze partial g, partial p in the same way, and each block in here will tell us how the f minus ma residual at time step I changes with respect to the jth input parameter pj. Now, the sparsity structure of this partial g, partial p matrix depends a lot on what p actually means. For some types of control problems where we have independent parameters for every time step, we can easily observe that partial G, partial P has a block diagonal structure that's very simple. And that means that we can employ specialized solvers to compute dxdp. We can use, for example, block forward substitution, and this will allow us to solve the system very efficiently. So once we have this information under our belts, we can once again take a look at a typical inverse problem optimization loop, where basically we begin by computing a change in the input parameters. If we're using a first order method, then we just directly use the Jacobian dxdp here, which we now know how to compute. Once we have a direction along which the input parameters need to change, we can do a line search on that. And once we update the parameters, we once again run the forward simulation step to get the configuration of the system at given the updated value of the parameters. Okay, so again, the Jacobian we can compute analytically here. Now, of course, as we've seen before, we have many other options. We don't have to be restricted to running gradient descent. Although this expression looks a little bit complicated, it turns out it's not very difficult to do something that we call second order sensitivity analysis to compute in the same way also a Hessian, basically the second order derivatives that will tell us how the value of the gradient of the objective will change with respect to the input parameters. And if we drop higher order terms, we can get to a generalized Gauss-Newton formulation. Again, these are all concepts that you've already seen in this course. Okay, so in order to summarize a little bit what we've seen so far, as a high-level overview, what we need for differentiable simulation is first and foremost a mechanical system. And in our own work on this topic, we focus mostly on multi-body systems composed of coupled, rigid, and viscoelastic objects. Just briefly, to represent the configuration of a rigid body, we use generalized coordinates, which encode the location of the rigid body's center of mass and its orientation in space. Soft objects that squish and deform under the influence of external forces are represented using the nodal degrees of freedom of an underlying finite element simulation mesh. And we can couple rigid and soft objects to each other through various types of spring elements. We are treating the equations of motion with fully implicit time-stepping schemes. This allows us to handle stiff systems without numerical instabilities, even when we're using relatively large time steps, and this does help a fair bit in reducing numerical errors that might otherwise accumulate if we're using a very large number of simulation steps. So what the mechanical model needs to output in order to use implicit integration is a definition of the forces that are acting on it, as well as the force Jacobians. Now, whether it is a constitutive law that governs the relationship between strain and stress, a Hookean spring, or a PD-controlled motor, the recipe for computing forces is largely the same. We start from the definition of a scalar potential energy, and forces are derived as the negative gradient of this potential with respect to the degrees of freedom of the system. And although the equations of motion do not have a closed form solution, we can use sensitivity analysis to analytically compute derivatives with respect to the input parameters P. Now, one crucial ingredient that is still missing is contact handling, which is of course very important for forward dynamic simulations. And contact handling is important because it is through contact and friction forces that physical objects interact with each other. Now, the simplest reasonable model of frictional contact that we have in physics is given by Coulomb's law of dry friction, which essentially states the condition under which there is no slip or no relative motion between two solids that are in contact with each other. This is, of course, the relationship between tangential forces or tangential friction forces and the normal forces that are making sure that the objects do not interpenetrate. Now, it's worth noting here that contact and friction are inherently discontinuous events. And if we want to still use a contact model in a differentiable simulation framework, then we have to smooth out these discontinuous real-life events and approximate them using smooth functions where derivatives are still well-defined. I will tell you how we do this, but first, I'll just show you this general picture of frictional contact, which I hope you are all pretty familiar with. Let's consider a large immovable object like a sphere here. We can use a scalar function like a sine distance field to be able to tell when a point is inside the object or when it is outside. So if we have a mass point that is moving through space and it collides with this object, then the way in which it bounces off is governed by contact and friction forces. So the contact forces will be acting in a direction that's normal to the surface at the point of impact. And so these are the normal forces, and the friction forces will act orthogonally to this force. So basically they'll be they'll be in the tangent direction. Now, these contact and friction forces cannot be arbitrary. They must satisfy certain constraints. The normal component of the force must satisfy non-penetration constraints, for example, which can be written down in this simple way. It just states that the normal forces cannot be acting when the mass point is outside of the body, of course. The normal component of the force has to be strictly positive. That means that the contact forces can only push the objects together, they cannot pull them back. And in magnitude, they should be just large enough such that, taking into account all the other forces that are acting on their system, it will allow for no interpenetration between this mass point and the object that it is colliding with. Now, for the friction forces, we also have several constraints, and these are given by Coulomb's law of friction. Now we can talk about the stick and slip domain. Basically, if we can get a friction force that makes the relative velocity at the point of contact 0, then that should be the right answer, as long as this force isn't too large. If it is too large, and this is basically a relationship that's governed by the magnitude of the normal component of the force, then the mass point will be moving in the tangential direction relative to the object it's colliding with, and the magnitude of the friction force will then be given by this expression. So the friction force must be opposing the relative velocity. Now, if we are to visualize the magnitude of the friction forces as a function of the relative velocity, they will look something like this. We can clearly see the stick and slip phases of frictional contact. And well, here we also see how this is just not a differentiable type of force. Now, luckily for us, we can apply a smoothing scheme, which formally is called a modification of the Coulomb friction model. And this allows us to smooth out the discontinuities that do exist in the natural world. So, for example, if we're looking at the magnitude of the normal force as a function of the distance field, the value of the position of the particle, Well, we can come up with a model that might look like this. So this is essentially a softmax function. Now, this force doesn't guarantee that penetrations never occur, right? So it's still an approximation, but at least we can make it smooth such that we can take derivatives of it. Now, similarly, if we're looking at the friction force that's given by a Coulomb model, well, we can come up with all sorts of approximations that capture the nature of this force, but allow us to also take derivatives. So we can come up with piecewise linear or tanh or sigmoid functions that, if we control the stiffness of these different forces, that in the limit, they get arbitrarily close to the physical phenomenon that we are trying to model. So all we now have to do is take this definition of smooth approximation of contact and friction forces, we plug them into our model, and then they can be handled like any other force that's acting on the system. Now, of course, an important question here is, how much do different modeling choices here matter? Can we get reasonably close approximation of frictional contact? Do they have an impact on the optimization problem and so on? And the answer to all of these questions is yes. There are many experiments that we can run here. I'll just show you two that we've gone through in order to try to understand these questions in some detail. And what we are seeing here is the same squishy object that is dropped on an inclined plane. And we can use sort of a state-of-the-art formulation of contact with all hard constraints versus some of the smooth approximations that I talked to you about. And it turns out that they behave in a quantitatively or qualitatively similar manner. At the same time, although we might incur some small errors, as it turns out, these degrees of freedom that we have that can be used to make the contact and friction forces more realistic, or on the opposite side, more smoothed out, will also have an impact on how smooth the optimization landscapes are that we are, the optimization landscapes that we are exploring during inverse control or design problems. So I'm going pretty quickly over all of this information, but the take-home message here is that there's a lot that one can do by exploiting the parameters that are exposed in the smooth approximation models. Okay, so with this type of smooth approximation to frictional contact in place, we can then compute forces and force Jacobians of contact and normal and friction forces. They get plugged into the equation of motion and into the sensitivity analysis that we're using to compute derivatives, just like all other forces that come from a mechanical system. And ultimately, then this allows us to solve inverse problems given motion objectives. And the outcome of the inverse problems that we're solving then is optimal values for the parameters that are an input to the forward simulation model.
Hi everyone, my name is Miles. Welcome to this section of the differentiable simulation course. I'm going to be talking a little bit about how we actually compute some of these derivatives for our simulators using things like order differentiation. And then I'll talk a little bit more about some applications and what we can actually do with these gradients once we have them. So just to introduce a little bit of my own notation, often the problem we care about can be described through a scalar loss function. S, that is a function of the system parameters x. And x is a vector that can include things like the system coordinates q, the time derivatives, and also some model parameters theta. And I'm going to just limit the discussion to loss functions that depend on the final system state. So this could be the state of the system at some point in the future after some amount of time has passed. And the system dynamics are governed by an ODE, usually a second order ODE. And this describes how the system is evolving through time. Just to kind of give a little bit of an example of this type of system, in this case, on the video on the right, we have a center particle suspended by some springs in space, and the goal is to make the center particle reach the blue sphere, the target. And in this case, the loss function S is just the Euclidean distance to target. And we'd like to optimize with respect to the model parameters, in this case, the rest lengths of the springs. And so if we can take gradients of our loss with respect to those model parameters, we can run an optimization. And here you can just see this optimization proceeding. And you can see very quickly we can converge to a pretty accurate answer using something like LBFGS, just through these first order gradients of our dynamics. The sort of problem is you need to somehow compute these gradients, and the question is, how do we do that? And some of the other speakers will have talked about how to do this in an analytic way. But I find deriving gradients particularly error prone and quite tedious. And every time you change your physical model, it means you have to go back and rederive them. So I think if we can automate this, then it's a big win for efficiency. And that's really the role of auto differentiation. And I'm going to talk about some different methods for doing that. So we have our scalar loss, and we would like the gradient of the loss with respect to our initial conditions, x at t0. And we can introduce some more notation and give this quantity a name. And we sometimes refer to this as the adjoint of x. And we call this x star. And x star really is just the vector of partial derivatives of s with respect to x. And so our goal is to compute x star at t0. Often we can assume that we're given x star at t1, that's the derivatives of our loss with respect to the end state, and we need to somehow get our propagate these gradients back to the initial conditions. So there are a couple of ways to do this. The first is something called the continuous adjoint method. And I said that our system dynamics are governed by an ODE. And this tells us how to evolve the system forward in time. It turns out with a small transformation, we can essentially find a way to propagate our gradients backwards from that end state back to our initial conditions through a reverse ODE. And so this is illustrated on the right. At the top in blue, we have the forward dynamics going forward in time. And on the bottom, we have the adjoint, which is taking our gradients backwards in time back to that initial state. And I won't go into too much detail on this, partly because I find the continuous adjoint method much less intuitive than some other methods. But this was the basis for the quite popular neural ODEs paper that was at NeurIPS a few years ago. So that's worth a read if you're interested in this method. I find it much more intuitive to really come at it from a discrete point of view. And here we're going to replace that continuous ODE with some time stepping equations. So we take our forcing function f, and we're going to replace it with a time stepping scheme. So f essentially represents our integrator. And now we have this piecewise linear trajectory where we have discrete states at each of these points in time, usually with a fixed time step between them. And we can describe this essentially as saying, S is a function of x at time t plus n, where n is the number of steps. And to get there, we essentially just nest these calls to our time integrator f, and we have this sort of recursive nesting. Now, if we want to calculate gradients of S with respect to those initial conditions, we can essentially just do this directly. Take this middle equation and apply the chain rule, and we get this, sequence of products to evaluate, to propagate our gradients back to the start. And again, you can see it's a direct analog to the continuous version in red, where each of these products essentially propagates the gradients backwards in time one step. There are two ways that we can evaluate this sequence of products and to evaluate the chain rule. The first way is called the forward accumulation method, or sometimes the tangent mode. And really, this is just a question of where do we put the brackets? We've got this big chain of products. How do we place the brackets to evaluate it? And in the forward mode, we do it in a sort of inside-out way. And we essentially have this sequence of matrix multiplies, where each of these Jacobians is being multiplied by the next one. And so the obvious sort of problem here is that, matrix multipliers are expensive. And so we would like to avoid this if possible. And that's where we turn to the reverse mode or adjoint mode. And sometimes this is also just back propagation by another name. But here you can see we've put the brackets around a vector matrix product. And when we do that, it means we only have to evaluate matrix vectors products, and that's much cheaper than the alternative. And this is partly why this has become such a popular approach for machine learning. It's also really efficient when we have many parameters. So we want to compute the gradient of a scalar loss, but with respect to potentially thousands of parameters, because we're just doing these matrix vector products, they're very cheap. So just to kind of put the continuous and discrete versions side by side, it's kind of nice to kind of see these on the same footing, I think. On the continuous version, we have the smooth trajectory governed by this differential equation with this integral term here and a forcing function f. On the right, we have a discrete trajectory and a discrete loss, which is a function of our time stepping equations, which have been nested in this kind of recursive way. And the continuous case, we have to, essentially solve this reverse mode ODE to take our gradients backwards in time. And in the discrete case, we essentially are evaluating the chain rule, and each of our matrix vector products is taking us one step backwards in time. The thing you note here is that both these methods, they still need the gradient of f with respect to x. And that's what we're going to talk about computing next. So if for the discrete case is our simulator, how do we compute a gradient of an entire simulator? Well, we can start just by looking at a simple function. So, given a function f of two variables, x and y, produces some new quantity we'll call z. And similar to what we did with the adjoint of a variable, we can define the adjoint of a function. And so the adjoint of f takes the same input parameters, x and y, and then also takes z star, the adjoint of the output, which we assume is known, and it gives us back the adjoint of the inputs. So it gives us back the derivatives of s with respect to the inputs. And it turns out that this only involves, again, doing some linear algebra based on the gradients of f. So this is like a building block. Like this is, once we can do this for a simple function, we can do it for much more complex ones. So let's have a look at some examples just to kind of see how this works. On the top row, we just have a simple addition. And if you plug the definition of the adjoint of this of a function in, you can see that it generates a simple has a simple definition where it's just passing back the adjoint of z, the output, with respect to each parameter. And it's same for the product rule. And this is just a sort of mechanical process of taking your function definition and plugging it into that the definition of the adjoint and deriving these sort of building blocks. The question is, of course, how do we sort of compose these into something, you know, more complex like a program? So let's have a look at a slightly more complex example. In this case, we have an expression sine A plus A times B. And we can write this as an evaluation graph. And so we can think about how we would evaluate this as a program. And we have A and B as the inputs going into the functions sine and multiply. And these produce intermediate values, C and D, which are parameters to the addition function. And finally, we get our output, yes. And so when we evaluate this in the forward mode, we're really, you know, traversing it from the left-hand side to the right, from inputs to output. The gradient, we can take the adjoint of each of these building blocks, the product and sine function, and evaluate them in reverse order. So we start, when we're performing reverse mode ordered, if we start on the right-hand side and we go the other way, and we start with the adjoint of S with respect to itself, right? So S star, and that is just one, right? Like that sort of, it can be thought of as the seed variable that we're going to use coming in on the right and passing it back into this graph. We then just call the adjoint of each of our functions with that parameter and propagate this left to right until we get back to A star and B star. And that's the answer that we want. We want S with respect to A and S with respect to B. And at each step, we're accumulating gradients onto these intermediate adjoints and these final outputs. One thing that is maybe not illustrated here, but is that, you know, to evaluate these adjoint functions, we had to store the input parameters to each of them during the forward pass. So if I just skip back, you know, the C and D that went into the add, for instance, we need them again to evaluate the adjoint of add as well. So this is one of the ways that reverse mode ordered if works, is that it usually stores these input values on some kind of tape, like during the forward evaluation for reuse during the reverse mode. I'll talk a little bit more about that soon. So that's sort of a summary of like reverse mode ordered, but there are a lot of different ways to actually implement it inside the computer. The first is the graph evaluation type approaches, which are really, I think, quite similar to the way that I just described it, in the sense that they explicitly build a graph of the evaluation or of the operations in the program at runtime usually. And then when you want the gradients, they reverse that graph backwards. And so the examples of this would be something like PyTorch, TensorFlow, and JAX. And these are all quite functional in nature, and they're all particularly tensor-centric. So every operation in the graph is an operation on tensors. And they're functional in the sense that generally they don't support things like in-place operations. And so you can't mutate variables, like every operation just produces a new output. And the second approach I want to sort of mention here is the program transformation approach. And this is slightly different in the sense that, again, it sort of, treats the program as a graph, but it performs a compile time transformation. And this typically allows a more sort of imperative, thread-centric approach to order differentiation. Examples of this would be things like Diff-Tai-Chi, Google Tangent is another, Tapenade, and my own library, which is called Dflex. And essentially what these do is they take some description of the program, maybe as an abstract syntax tree. They traverse that at compile time and generate the adjoint of the program, which is then compiled to some machine code. The third approach here is the symbolic approach, which is what you might find in something like MATLAB, Mathematica. And this is often based on things like expression rewriting. And it's typically limited to continuous functions without control flow or anything like that. But this can be really useful for deriving the building blocks of your differentiable simulator. And in fact, I think that all three of these approaches are very useful. And I think a nice way to think about it is sort of like a three-level hierarchy. So at our top level, we have the computational graph, and this might be something like in PyTorch. And that's maybe how you write things like your loss function, or you describe your neural network. And in the middle level, each of these nodes in the PyTorch computational graph has to do some work, usually maybe done by a DPU kernel. And so we need the adjoint of that kernel. So we want a forward and a reverse mode of each of our kernels. And each of the kernels in turn consists of functions like the sine, cosine, dot product, cross product. And so we need the adjoints of those. And those mathematical primitives are where we might bring in our symbolic tools. So top level, we have a computational graph, the graph-based approach. Mid-level, we have our source code transformation approaches, and bottom level, we have our symbolic approaches. And a sort of example of this is maybe just a simple spring-based integrator. And we have one kernel for calculating our spring forces, one kernel for calculating contact forces. We plug both those into an integration node in the graph, and the output of that goes into a neural network and a loss function. So I want to talk a little bit more about the program transformation approach, because I think this is particularly well suited to simulation code. And this is that middle level that I kind of talked about. And one way to, just to restate the problem, we have some description of a program or maybe just a single function that we care about. For example, calculating spring forces, and we want to find the adjoint of that function so we can compute gradients. So a simple sort of pipeline for how to do this would look something like this. We're given the abstract syntax tree of our function, and we assume that we have some parser that we can obtain that with. And if you're in Python, it's actually very easy using something like the AST module. A couple of lines of Python, you can get the AST of your function. We can perform like a depth first reversal on that and convert it to something called static single assignment form. And this is a sort of sometimes called straight line form of the code. So, we basically, again, don't allow mutating variables. We just have each line of the program now will take some inputs and generate a new output. And we get a flat list of code. And so when we want to run the function forward, we just execute this list of instructions. And to run backward, generate the gradients, we just run that same list in reverse mode, in reverse order, calling our adjoint functions. And I'll show an example of that. So if we just take that simple expression that I described earlier, sine A plus A times B, this is what a program transformation approach to order diff would generate, for example. The simple reverse kernel at the bottom is what you would have generated by a source code transformation order diff tool. And you can see that essentially in the forward mode, first of all, we declare some variables, but in the forward mode, we evaluate our expression, sine first, then a multiply, and then we add them together. And each variable is stored along the way. And then to generate the reverse mode, we're going to call in reverse order the adjoint of each of those operations. So we have add, mul, and sine. And each of these adj functions is essentially like a built-in building block that we assume is available. And these are easy to derive. And so the nice thing about this is that unlike some of the graph-based, tensor-based approaches, all the state here stays local in the function inside the kernel. So this is quite efficient for GPUs, especially because we don't have to go back to global memory. And one of the problems with graph-based approaches as well is that they tend to generate a lot of kernel launches, because even just adding two vectors together is like one kernel, but it doesn't have a lot of computational density to warrant a full kernel launch. And so in this case, we can essentially fuse all these operations into one kernel in a way that's implicit in the way that the function is defined. And it also allows us to be a little bit more flexible on things like indexing into different parts of the arrays that might be input to us. So, we can also do this. In this example, I've showed a Python definition with a small decorator on top, df.func. And we can do runtime JIT compilation into this kernel-based output, and then pass that to something like MVCC to generate our CUDA kernels and launch this at runtime. So the transformation itself is generally very fast. It doesn't involve a lot of work. And just to kind of show how effective I think it can be, is that this is a more complex kernel that evaluates the bending force for two connected triangles. This is a very common force model in computer graphics for cloth simulation. But you can see it's relatively complex in terms of implementation. It has a lot of nested expressions. It has a few random access load and stores, and deriving gradients for this has been the subject of entire SIGGRAPH papers. So this is not a trivial thing to differentiate by hand, but with our program transformation approaches, we can do this very easily. And just to sort of describe at a high level, in some pseudocode, like how we do this, I think just to give a little bit more detail on the algorithm, if you want to implement this yourself, given your AST, assume we're doing it in Python with a Python AST, this little code snippet essentially shows you how to generate the adjoint of your function. We take our root node as input, and we're going to do a depth first reversal. And every time we receive or evaluate an operation, we're going to push back the output onto our operations list, our forward ops. And when we want to replay it, we're also going to push back the adjoint of that operation. And so all we're assuming here is that for each node that comes in via the AST, we know how to convert that to a forward mode and a reverse mode function. And generally, you just need a small library of building blocks to call to support quite complex programs. The nice thing about order differentiation is that it's relatively easy to check that your program, that your algorithms are working. We can use things like torch auto grad check or grad check, and this essentially just evaluates the full Jacobian of a function by repeatedly calling the reverse mode order diff. So one call for each row of the output. And this is just a little debugging tip. I mean, if you're implementing this yourself, I really recommend using these tools just to sanity check your gradient. If you're interested in the program transformation approach, I think I really want to give some credit to Taichi from Yuan Ming, which is a great framework and has some really nice examples in the original paper as well. I think really popularized this approach for graphics. And for some more detail after that, I think the textbook here is also great for discussing the program transformation approach. I've described the very, very simplest version of it, but you can get quite far with this. There's a lot more you can do in terms of optimization, but my philosophy on it is that you can do a naive transformation and generate something like C++ or CUDA, and then let the compiler do the heavy lifting of optimization. That's, you know, GCC or MVCC can do all the really low-level machine level optimizations, as long as you can generate a high-level description of the adjoint. And so this is a sort of transpiler type approach. Okay, so I think now is a good time to talk about some simulation, talk about some examples and applications and things that we can do with our gradients. And, you know, I didn't specify really any particular time integration scheme yet, but auto differentiation methods are particularly well suited for explicit time integration. And in particular, I think a good choice is the semi-implicit Euler or symplectic Euler method. And this is a simple one-step integration scheme. And essentially we evaluate our forces at the current position, and then we update velocities and update positions. I just noticed there's a missing nabla on this psi here, so we should take the gradient of our potential function psi. But we can describe the entire semi-implicit step as f. We're just going to call that these two operations as f. It's a function that takes our current position and gives us our next one, or system, our current system state, and gives us our next system state. And again, our goal is to differentiate through f to obtain the gradient of our loss with respect to that input parameter. Once we have that gradient, we can just apply our favorite numerical method, you know, gradient descent, some quasi-Newton methods, or even some, you know, conjugate gradient nonlinear methods. And compared to sampling-based approaches, gradient-based optimization, you know, there have been some experiments to show that it can be, you know, 10 times more efficient than sampling-based methods. So generally, you know, it's worth having these gradients. Here's a small example. The goal in this scenario was to choose or find the initial velocity to throw the cloth such that its center of mass passes through the target at some point in the future. And here, I think we optimized with LBFGS, and you can see that in just a handful of iterations, it learns to throw and find that initial velocity that causes it to pass through a target. And I think this is pretty neat because, you know, the dynamics here is relatively complex. We have a nonlinear lift and drag model, like nonlinear, you know, constitutive model, and with a pretty simple optimization scheme, we can solve this problem pretty quickly. With the thin shells, just to talk about some of the physical modeling we can do, we can use like a thin shell FEM model with that bending energy that I mentioned earlier. And we can have activation or actuation parameters that go into the bending modes, as well as the lift and drag model. So here, this is a little jellyfish that I modeled up in Blender on the right. And the goal was to teach the jellyfish to swim by actuating its bending modes. And so we can write a small like neural network to do open loop control on these parameters. The network is parameterized by time and has some sinusoidal inputs that go into just a single layer neural network. The output of the network goes into our integrator, and that takes us through a semi-implicit Euler or a sequence of semi-implicit Euler steps to produce our final system state and then into a loss function. So here's the example. This is using the randomly initialized network weights. And you can see that the jellyfish doesn't really do much. It is sort of doing a little bit, but it's not really going anywhere particular. The goal here, the loss function, was, I think, just the vertical velocity at the final, or the vertical displacement, to try and get the agent to move upwards as fast as possible. After around, I think, 100 SGD iterations, it learned this policy. And so you can see, I think, it's fairly effective at learning locomotion, even again for these complex dynamics. And in this case, it's open loop control, so you can see that it gets a little bit off course. But this is the type of thing you could play with and have some observations coming back into the network as well. A solid FEM, we can implement things like Pixar's stable neo-Hookean model inside this type of order differentiation framework. And now we have an actuation parameter on volumetric strain, essentially, so we can control expansion and contraction of each element. And so this mesh on the right is just a sort of a tire, a wheel, and we can again use an open loop controller to actuate each of these elements individually over time. I think this has around 1,400 tetrahedra, and the network outputs a unique actuation value for each one. And in this example, the goal was to roll along the x-axis as far as possible in some fixed amount of time. And you can see this is the initial policy that it started with. And I think this was LBFGS as well. See, after just a handful of iterations, it actually learns to locomote pretty effectively along the x-axis. So a more complex example here is this volumetric bear, voxel bear. And again, this is discretized into a tetrahedra with the same volumetric actuation terms. And using an open loop controller, we can actually learn pretty robust gates for this bear model, even though there's quite complex contact and friction dynamics happening here. This was optimized in just a few hundred gradient-based steps. This example is from the ECNU Seoul National University humanoid model. And the goal here was to actuate each of the muscle tendon units on the body, on the upper shoulders and the neck, to cause the head to look at a target. And so just starting the optimization process, you can see initially it just falls. And here I'm sort of fast forwarding through the optimization, and you can see pretty quickly we learn how to optimize these muscle units to achieve the goal. And so here pink means actuated and blue is unactuated. And so I think this is potentially a useful direction for physically based animation and character-based animation. I want to talk a little bit about contact. I think Bernard's also going to discuss this in some more detail, but generally for differentiable simulators, especially with an explicit integration scheme, we want to use something like a penalty-based method of contact. If we treat if we treat it like a exact contact model with zero interpenetration as which would be like the green line here, this would be something like the LCP type model. We have this hard step function, and so we can change that to like a hinge function by using a penalty force proportional to the penetration depth. And we can achieve higher levels of smoothness just by exponentiating this contact model. And this can be important just to smooth the optimization landscape, because most of the examples I showed, although they work and you can get the optimizer to converge in many cases, they're still sensitive to local minima, and problems often arise through the contact functions. So if you're having trouble with optimizers converging, there's a good chance that you need to regularize and smooth your contact functions. And the same approach works for frictional forces. If we treat Coulomb as the exact model, we have this hard step function. We can relax this and have again a hinge or a smooth approximation as well. An example of differentiating through contact. The goal here is just to get the ball to bounce through two contact events and hit this black target, and the colored lines just show the optimization process proceeding and how we converge to the solution. The problem, if you look carefully at this example again, the problem is, well, the sort of trick to get this to converge is that there's two contact events in the initial trajectory. So the initial trajectory hits both balls. Now, if you imagine that it didn't hit any of the balls, you would essentially have a very flat region in your optimization landscape. And so you can imagine here another scenario with two billiard balls, and the goal is to hit the red ball into the green one such that the green ball stops on the X. Now, if your initial guess at the impulse on, or the velocity of the red ball is such that it doesn't hit the green ball at all, then you're in this very flat regime where you have zero information about how to move in the loss function. And it's not until you align towards the green ball enough such that you get at least one contact that you start to get into this this region where the gradients are useful. And so this is, I sort of refer to this as like a contact sparseness problem. And it's very easy to sort of fall into this this kind of trap where your optimizer will just not converge if the initial guess is too far from the solution. The other problem with contact is contact generation. And so, in a physics simulator, contact generation is really this computational geometry problem where we're given, two meshes as polygons, and we want to get out things like the contact points and normals that represent the overlap between them. And this is some of the sort of hairiest and nastiest code that you might find in a simulator. And it's very autodiff unfriendly, I would say. So I think, we need to look at alternatives. I think signed distance fields are one such alternative that is very promising. And so you can imagine this example on the right, where we're dropping the ball and we want to know where to drop it such that it hits a target. For this optimization to work, we need to understand how that normal at the point that it hits is changing with respect to the initial conditions. Otherwise, we don't know how the final state is going to change as well. And so I think in a lot of the diffsim work that's been done so far, these types of contacts are treated as sort of fixed over the course of the time step, and we don't necessarily differentiate through them. You can imagine one way to do this would be through SDFs, where we just look at the normal as the gradient of our signed distance function, and then the adjoint of that normal is also quite easy to compute. We just need to take this the Hessian of our signed distance function and multiply our adjoint coming in. So I think SDFs, this is something I haven't implemented myself, but I think that we're going to find that SDFs are very useful for our differentiable simulators. And this is just a small example. This is not differentiable, but just to show the sort of power of signed distance field collision. It's very robust, and we can handle really complex models. I think that if we can also make this differentiable, it's going to open up a lot of possibilities for design optimization and physics-based animation. Another question we asked recently is can we connect our differentiable simulators, our physics simulators, with a differentiable renderer? Both of these things have non-smooth functions. In theory, we can get end-to-end differentiability, but are the gradients really useful? And so we took this unified view of simulation to mean not just the physics side, but also the differentiable rendering side. And we used the techniques that I've talked about to write a differentiable simulator in PyTorch. And then hook this up to a differentiable rasterizer. And there are quite a few of these available now. And these essentially work by using a soft rasterization type approach. And when we do that, we can essentially construct an entirely differentiable pipeline that takes us from our model parameters through the physical state into the displaced triangle mesh. And then we can write our loss function on pixels themselves in the image space. So literally taking a target image that could be synthetic, it could be a captured image, and looking at the pixel-wise error between our synthetic rendered image. And given that pixel-wise loss, we can propagate gradients all the way back through the renderer, back through the simulator to our model parameters. Here's an example of using this to estimate contact parameters, like the frictional and stiffness parameters of contact. Given a ground truth, which is a synthetic sequence, we take an initial guess from some point, and we're obviously quite far away from it. After some amount of optimization, we managed to achieve a really close match. And again, this is just through pixel-wise differences looking between the desired image and the final one. We can do the same thing for elasticity parameters. Here we're just optimizing the Young's modulus given some target shape that we want to match. Our initial guess might be quite far off, but after some optimization, we can match it quite closely. And these are, all based on synthetic ground truth. But like I said, you can imagine extending this to captured images as well. And I think with some, suitable segmentation on your capture and your synthetic render, I think these loss functions will generalize to more complex scenarios. We've also been doing some work on differentiable cutting simulation. And so in this work, the goal was to come up with a smooth cutting model because, cutting, is sort of intrinsically non-smooth, right? Topological changes. And so we came up with a cutting model where we essentially introduce a smooth damage between FEM pieces using a spring model. And what this lets us do, we actually had some measured ground truth force profiles for cutting different vegetables. And we were able to optimize our model to fit that data quite efficiently to get predictive simulations. Once we've matched our model to the captured data, we can also optimize the cutting motion to minimize the force required to cut through an object. And this, the interesting thing here is that it actually gives rise to this soaring motion that you typically use when you're cutting in the kitchen. So, I think this is just an example of the power of differentiability, not just for the parameter estimation side, but also for the control optimization. I'd just like to finish talking about, again, just some of the challenges with differentiable simulation. I think local minima are endemic in what we do with simulation. And I think a nice way to kind of get an intuition for this is just to think about a block of jelly resting on a table, and you give it a small push, and it oscillates around some point. And each of these oscillations is essentially like a local minima that you can potentially be trapped in. And this is really a direct analogy to what happens when you try and optimize for these types of problems. And the image on the bottom here is from an RL locomotion example, and we were just perturbing one parameter in the neural network, looking at how that changed the loss function for within some small epsilon. And you can see just how noisy it was. And so, this is a real problem, that the loss landscapes that we have are just so noisy with so many local minima. We need more work to figure out how to actually explore these and optimize them efficiently. So I think that will almost certainly require some combination of stochastic exploration with gradient-based optimization. I talked a little bit about explicit time stepping, and the big downside of explicit time stepping is that it requires generally more memory, because each of your time steps need to store the input state and the output state for every step. And so for things like robots, which only have a few degrees of freedom, this is not such a big deal, but memories can quickly explode for complex models like FEM with many particles and cloth. And especially when combined with long trajectories and small time steps, this is a big, potentially a big problem for explicit methods. A few sort of solutions are things like checkpointing. So PyTorch in particular is nice because it has a built-in checkpoint mechanism, and you can essentially save out your state and then replay up to replay from that point to recreate these intermediate states that you need to run the backwards pass. I think also, something that is related that needs to be explored would be, how to use AutoDiff to efficiently compute or to solve the implicit time stepping schemes. Typically, these require like a Hessian of our energies, and that is something that's still relatively expensive or much harder to do efficiently for AutoDiff. So I think there's potentially some work to be done there as well. I just want to finish with some references that I mentioned during the talk, and thank you very much for your attention.
Hello everyone, my name is Nils Thürer from the Technical University of Munich, and in this fourth part I want to talk about differentiable simulations in the context of fluid simulations and also make the connection towards deep learning. All right, let me motivate this a bit more broadly. These fluid phenomena that I want to focus on in the following are everywhere around us. So starting with the air you breathe in the room you're sitting in at the moment, a very classical topic being flows around airfoils as shown here at the bottom, but interestingly also things like water. Maybe you have a glass of water on your desk at the moment. All these actually follow very similar descriptions, and that is what I'll be focusing on in the following. There are actually very interesting connections towards robotics. We already heard about that in the context of fluids. For example, it would be really interesting to have articulated swimming fish interacting with fluids, but also from chemical reactions to thermodynamics, plasma physics, medical simulations, the blood flow in our bodies, which are typically made up to a large majority of water and fluid-like substances, actually all behave under very similar laws. And this is what I want to focus on in the following in the context of differentiable simulations and deep learning. And I want to take a fairly pragmatic standpoint here. So basically using these physical laws as a starting point, also keeping all the numerical methods that we have in the picture here. I think they're very powerful tools, but combining this also with machine learning techniques. And in a way, first sight might sound a bit trivial or so, but in a way, this machine learning can kind of clean up and give us the transition from these idealized computer-based descriptions towards real-world applications, whether that's matching observations, interacting, controlling, or reducing numerical errors in the simulations. Yeah, so in this intersection, I also want to point out that we can distinguish different types of problems. It's good to mention before coming to the specific examples later on. So we have our physical systems, we have forward simulations where we set up a simulation with initial conditions, typically then let it evolve over time. And closely related, we have inverse problems. Here we typically have some derived quantities that we're interested in, that we want to optimize for. For example, the drag coefficient of an airfoil might be a classical example. And in these inverse problems, they're typically still based on a physical simulation, but we have some optimization loop around it, and they often are orders of magnitude more expensive. And we have already seen quite a few nice examples here. In a way, what we're talking about in this course is especially interesting in the context of inverse problems. So nonetheless, they share a lot of similarities. And now one of the main questions is, how do we actually integrate with deep learning? So the kind of the most shallow, superficial coupling, nonetheless an interesting one, is what I'll also later on call supervised, so purely based on the data. So in a way, the learning process here doesn't know much about the physical system. We can integrate a bit more tightly with loss terms. This basically leaves most of the training intact and then appends a few additional constraints at the very end in the loss. But what I think is actually the most interesting approach, and the one that we focus on in this course, is what you could call interleaved with these differentiable simulations that you've already been hearing about a lot. You can really get the learning and the simulations work very tightly together, and that actually gives the tightest integration of these different variants. So something to aim for, and something that I'll come back to later on in this chapter. Yeah, so also worth mentioning, there's by now nice variety of works that have looked at just this combination of fluids and deep learning approaches. Quite a few of them by now actually do use these differentiable simulations. Here you can find a few papers. I don't want to go into all the detail here of the previous work, but focus on a few examples from my own group, basically. But please look at these other works if you're interested in a broader picture and in additional background topics. Right, so how do these differentiable simulations work? Let me start with a very rough overview before going into the specifics of what fluid modeling and then also this deep learning connection. In my chapter, I'll use the following notation. We have a PDE description P and some phase-space states of a system, for example, the velocity of a fluid denoted by S. So this can be high dimensional, discretized on some mesh or grid in the following. And now the key quantity in line with the previous chapters is that from this PDE description, we actually now can get a gradient. So we want to know, given some input of P, we'd like to be able to compute the derivative with respect to S, telling us how do we actually need to change the input of our solver such that we get the desired change in the output. And one of the key topics of my chapter here will be that in a deep learning context, we can actually very conveniently combine this with learning. So just to give you a look ahead, if we have some loss function L and a neural network, NN, that gets an input and provides us some physical state S, given some set of weights theta here, then as you can see here on the right-hand side, actually starting from the far right-hand side, we have the derivative of the loss with respect to P. Then we can get another Jacobian to be specifically to obtain a gradient with respect to S, and then multiply it again with a Jacobian for S to theta. And in combination, this is actually something that we typically use in the training of a neural network. And this partial derivative based picture fits very nicely into the differentiable simulations we've been talking about. But I'll come back to the specifics in a moment here. Yeah, so key requirement, of course, is that this PDE that we're looking at, the simulator, gives us a derivative. It's not always the case, but if that's possible, then we can actually achieve a very tight integration of a physical system and such a learning-based optimization. And that will really be the larger goal of what I'll be talking about in the following. All right, so much for the introduction. So let's look at fluid simulations specifically. Here in computer graphics, you have a variety of traditional numerical methods to solve the Navier-Stokes equation. So here you can see it on the top right. In the compressible form, we have an advection term on the left-hand side with a material derivative, capital D, u dt, then a pressure term, a viscosity term, and on the far right, divergence of u being 0, the divergence freeness constraint. So there's actually a variety of powerful techniques here that we have at our disposal. In graphics, we typically employ operator splitting. So we have the advection step, the du over dt, solved in isolation with equal to 0, and then separately we enforce divergence freeness with typically a Poisson solve for the divergence equal to 0 constraint on the right hand side. We could of course also incorporate viscosity. That typically means we need to employ additional solving steps in the procedure, but for now, for simplicity, we'll leave it out. It's actually quite analogous, and there's a variety of nice methods available here if you're interested. But yeah, let's first actually look at the viscosity. Leave out the viscosity, look at the advection as an example. So the setup here is the following. We are advecting a passive density field D So it's called density here, but imagine it like a color density. It's not the actual density of the fluid. A velocity field u. And now our physical model, our PDEP, performs a time update. So the state of d at t plus delta t is the variation of this operator p given d at time t, our velocity, and the time t plus delta t. Now, to solve that, actually, we need to basically just unroll this material derivative, write it out from the previous side for our scalar density d now. And that gives us what you can see here at the bottom, the time derivative plus u dot gradient of d being equal to 0. So this is what we need to solve now, just looking at advection. We need to discretize it in the following. Actually, for simplicity, I'll stick with the simple upwinding scheme, but Semmelgrunge would be analogous and unconditionally stable, but I hope the upwinding will nonetheless nicely illustrate the process, because the whole goal here is not so much how we compute the advection specifically, but how to make it differentiable. Keeping that in mind, what's also important is why would we want to do this, right? Why need a derivative? So let's assume we have a simple optimization problem to motivate computing the derivative. Let's assume we want to match this density for some time, specified end time te. It should look like a certain shape. Right? Movies, it might be supposed to match a human figure or so. So the density state d target should be matched at end time, and we're starting at t0 with some initial density d0, indicating our initial configuration. Now we need to somehow evaluate how well we're doing at the end time. In the simplest case, we can do that with an L2 loss. So we're computing the two difference between this target state and the final state of our simulation. And with the previous notation, now we are evaluating this advection operator p, starting with d0 and our velocity field up all the way to the end time te. And now we want to minimize the velocity such that we match that target density. It's in a way a very simple inverse problem in this context, but it gives us a starting point of something to look at. So let's imagine this is now something we'd like to solve. Then, right, how do we actually get our velocity that does it? Well, this is exactly where the gradient comes into play. If you look at this minimization problem, we basically have a loss evaluation for our PDE solver P, which gives us the D. So essentially, we're interested in knowing how L changes with respect to D, so partial L, partial D, and then multiplied, chain rule, with the evolution of D as given by our PDE with respect to U, so partial D, partial U. Here it looks quite harmless and simple, and the reason I'm writing it out like this here is that the first part on the right hand side for the loss, that's simple enough. We have an L2 loss here, so for a square distance it just gives us the difference between the density at time t e, or end time, and the target with a factor of 2 from the square. The main challenge here is the partial derivative of d with respect to u. So this is where now the advection plays a role. So this is what I want to focus on. But this gives you a framework how this would later on fit into a simple optimization problem. So now we can actually look at our advection with a few more specifics. Assuming we're using this upwinding scheme, it can be written in the following form. So the new density for one specific cell I at the new time step is actually given by the old one, di, omitted the t, the notation of t here for simplicity. All of the terms on the right hand side actually for time t. And now for upwinding, we have this distinction between a positive and negative velocity. So basically, if you think about it, we need to look backwards in the flow, right? If something moves towards the right, we need to look at the left side where things came from. So for a positive velocity, we're actually looking at the negative side, and for a negative velocity, we need to take into account the indices on the right hand side. So here this is illustrated again visually. In this example, we're actually looking at the case on the right hand side. So we have a velocity that is less than 0 moving towards the left. Then we're basically looking at di and di plus 1 as a stencil. So for this negative velocity, we'll actually get the expression at the bottom. In this case, it's 1 plus, and then the actual, you can see it as an interpolation factor from the velocity. We have ui over dx, giving us the relative velocity within the cell times delta t for the current time step. Keep in mind this is negative, so we have 1 plus something negative for di, and then minus minus, giving us a positive factor for the di plus 1 on the right hand side, on the right side of this equation here. This is what we actually get for the first order upwinding here for one cell, just to give one example. And now this is the expression we'd actually need to differentiate with respect to the velocity u, right? Keeping in mind our optimization goal, we're actually now interested in the derivative of the previous slide. It was the density. We have p as a function giving us a density, so we have partial p with respect to our velocity ui, partial ui. And if you look at this, we're just left with the terms for ui, which in this case is dt over dx, di minus dt over dx, di plus 1. So we're basically getting a scaled finite difference, or if you want, a density gradient for the influence of u in that particular case. So negative velocity is basically in order to achieve a certain effect with respect to the negative velocity, the di and di plus 1 are the quantities influencing that particular velocity entry. And yeah, this we could now repeat for all the velocities in our grid. In 1D, that would be just one line, could be 2D or any higher dimension. Keep in mind, due to the direction, we might actually have to accumulate components, contributions from different cells in first order, just in the direct neighborhood of a cell, and those all would give us the final gradient for this one particular velocity entry. But anyway, the key message here is this is not too difficult. These are quantities we have. The derivative is just a fairly simple first order derivative that we need here, and this can be computed straight away from the entries in our density field and the corresponding values being influenced by a certain velocity. Yeah, you can actually see this a bit more generically if we look at our operator p for this advection as a bit more abstractly for a certain time step. Then no matter what we're doing here, we can linearize this for one time step, right? No matter what's happening here, we can basically encode whatever process is happening in our operator p for one time step in a matrix. So here, for simplicity, just call it A. Now, if we imagine we're basically writing out what the advection operator encodes in this A, then the gradient, the derivative we're after here for u, is basically just A transpose. So the transpose of that matrix that gives us the update here, that is what we're looking for. And this viewpoint actually can be helpful. In many cases, it's possible to compute this in a matrix-free form, so we don't actually need to set up this potentially very large matrix, right, it would be full. We'd have a squared number of entries in terms of the degrees of freedom of our system. But in many cases, it's fairly local, and we don't actually need to allocate the whole matrix explicitly, but rather we can often accumulate this transpose step by step while evaluating something like an advection operator. So this is something to keep in mind when implementing these in practice. Yeah, also in my example just now, I've just described one single update step, right? One evaluation of the upwinding scheme. Of course, we are not limited to these cases. We could have an arbitrary number of variations of our advection operator. So I want to write it out here for one example, assuming a constant velocity for now. Of course, also the velocity could change over time. But let's assume we have a certain number of steps towards this end time t that I mentioned before, and we want to match the density at the very end of the sequence. If you now write that out, so now we have basically again the loss, then our operator p, but we have a whole sequence of evaluations of our PDEP to update the density all the way towards the end time. If you now apply the chain rule, you'll actually get this on first sight relatively unwieldy expression. But if you look a bit closer here, there are actually a lot of very similar terms. So the evolution of this density is given by the advection, and over the course of the whole advection, we're interested in how does each of these density states contribute to the velocity. So it's actually easiest to see if we look at this whole chain of evaluations of the advection, and then imagine we basically have branches off towards the velocity. So keep in mind here, we're assuming the velocity is the same for all of these evaluations. So the key here is actually this longest chain of derivatives at the bottom. So here, if you look at the right-hand side, we have again the loss, partial d at time t end. Then that is multiplied from left with the Jacobian for end with respect to end t e minus delta t, then minus 2 delta t, all the way to t0. And for this one term, at the very end, time 0, we actually have one derivative with respect to u, but we basically have these branches for every state of our density where we get the derivative with respect to u, the velocity, and these actually match the ones at the top here. So if you look here, we have one term for te minus delta t, and the top one was actually the very first one, the end time, if you want, of the evolution. Here we have the end evaluation of the last step being derived with respect to u. So you can imagine that basically unrolling this chain of calls of our advection operator and then just computing a branch of the side for the derivative or the influence of that density state to u, right, to basically kind of map the information from the density states to the velocity. So in a way, the important point is here, this is once we can compute one step, we just have a sequence of those, and we can easily evaluate arbitrarily long sequences in a very similar manner. Yeah, so to look ahead, right? We actually don't need to explicitly code this up, but because we have so many similar components here, we can treat these gradients in a modular fashion and reuse derivatives of d over time and then the influence of d for u. We can come back to it for the deep learning outlook, but because our loss is typically scalar, we actually always have this partial L, partial some input to L is always a vector form. The Jacobian here takes the form of a vector, and hence if we multiply it from the left with some other Jacobian, we actually keep a vector on the right-hand side, and hence we can basically treat this as Jacobian vector products, which is also what most deep learning frameworks do, and evaluate these chains for unrolling very efficiently. All right, so much for explicit steps. The pressure projection is interesting because it's computed in practice in a slightly different manner. So here we can't just evaluate one analytic expression to give us the next step, but here we have a system of linear equations that we need to invert. So in practice, we get a Poisson equation for fluids taking the form of the Laplacian of our pressure P being equal to the divergence of the current state of the fluid. And here this is summarized a bit. If we rewrite that and call the divergence term B for the right-hand side, and bring the Laplacian over to the other side, then we get the pressure P being equal to the inverse of the Laplacian times the right-hand side, or in the following just written as A inverse times this right-hand side B, whatever that is at the moment. And in this form, A inverse times B, it looks quite simple. Of course, in practice, we need to set up this matrix and then invert it with some suitable solver. But for the derivatives, it's actually surprisingly simple, right? And the right-hand side term, this B, is practice for fluids actually given by the divergence. So keep in mind, if we are now interested, as before, in our velocity as a quantity of interest and the gradient with respect to the velocity, then again we have some loss term, and our pressure as a key quantity here influencing our solution from the Navier-Stokes equations. And in this equation now, if you look at the original one, A inverse times B, the right-hand side B, that is actually what contains the velocity. So we actually also need to include in the end, the discrete version of the divergence, but I want to focus on B here for simplicity. The divergence is just one additional operation. If you just look at how the pressure changes with respect to B, then this is just this A matrix A, or here specifically the inverse. We're multiplying with A inverse. That gives us the new solution. And now if we compute the derivative of this operation, well, partial P, partial B just leaves A inverse. So down here, we basically get A inverse times partial L partial P, which is this vector that we get from the loss evaluation. And the nice thing now is this A inverse is really the same matrix that we have from the forward step. And the forward step is just a regular simulation. In practice, we'll probably have a nice and efficient solver to compute the pressure component, and hence we can actually reuse exactly that solver just with a different right-hand side. That is now given by the vector coming from the partial derivative of the loss, but it has the same shape because it's a vector with respect to P. We can directly use that vector as an input to our solver and use it to compute the resulting Jacobian vector product, and then basically pass that along the chain to keep on working with it. So in this case, this is actually very simple, in a way even simpler than the advection step to implement in practice. Yeah, some considerations here when computing all these derivatives. We could, of course, think about doing something like a conjugate gradient solver just within a deep learning framework. After all, conjugate gradient is nothing but vector operations, matrix vector operations, which you could, for example, implement with TensorFlow or PyTorch. Theoretically, we could do this. In practice, it's not a good idea because every invocation of one of these operators in a deep learning framework is actually tracked and registered. And hence, we would keep track of all these intermediate states of, say, a conjugate gradient solver, such that we could backpropagate through them, which is not necessary in practice. So as seen on the previous slide, we're actually not interested in all these intermediate steps. We might have 1,000 conjugate gradient steps. We don't care what happened in these. We're just interested in the matrix A inverse. That's what we need to have for the forward pass, and then also for the gradient in the backward pass. And hence, it's really important not to have a lot of overhead for these. Thus, in practice, it's actually a good idea to use custom operators that really only give the gradients at the right granularity, at the right intermediate steps, like after the pressure solve, after the advection step, to get a good performance. The first version could be a good starting point, can be nice for debugging. This also should give a first version, but this will be very slow. And in practice, we can do typically much better by providing a custom operator that skips the gradient evaluation in the whole SIGA solve and just computes the gradient for the final state of our system. Yeah, the viscosity solve, as mentioned before, would work analogously. And with that, I want to come to the next topic in the sequence. Yeah, the next chapter is how to integrate what I've discussed so far with deep learning. In a way, this chapter will be shorter. It's actually very simple. With what I've described so far, we can directly integrate these gradients that are computed for the simulation into deep learning. So we've just looked at the derivative of some solver P with respect to the state. The example is previously the velocity u. But if you think about what happens in neural networks, they actually also work with exactly these Jacobian vector products. So here we don't have a solving step or so, but we might have a, simplest case, fully connected layer, some weight matrix that is multiplied with an input vector. Or we might have something like a ReLU function, of which we need to evaluate the local derivatives, or a sigmoid or so for the activations. But all these are chained together in exactly the same way. We always have a scalar loss at the very end, meaning we just need to compute all these Jacobian vector products for a chain of evaluations. Yeah, key is the scalar loss. This is always the case for learning. We just have one single loss value, meaning the Jacobian at the very far right side is a vector, and hence if we unroll it reverse mode from the right, we'll always just need to keep track of the resulting vector after the Jacobian vector multiplication. Yeah, in practice, a bit like with the advection example before, we'll have some chain of calls. You can really see it in an implementation, from an implementation perspective. We have a chain of calls that we need to unroll with the chain rule, and then we get similar expressions where we basically evaluate the chain rule by multiplying from the left with Jacobians. Right, and this works in exactly the same way for the layers of a neural network as it does for different steps in a fluid simulator or any other simulator that is. Yeah, so let's look at a simplified example to write that out once. If we have some solver P that gives us a that takes some state S as input and produces another state S as output. So here we have Si for input, So for out, and we have some loss function that takes this output and compares it to some reference output S tilde, the So tilde here in the middle. Then, simplest case, right, just like before, we can actually look at a L2 norm, assuming we already have discrete versions of these two output states. And let's assume for simplicity here that the input, the Si, is actually given by a network. So the network gets some input X. Traditionally, it's called f of x or so in the literature, and the weights are typically denoted by theta. So the neural network is conditioned on these weights theta. With these weights, it produces the input for our simulator. Then if we put that together, we basically can say we're starting with a mini batch. We have some samples denoted by j. We're starting with one xj in the middle. This is provided to the neural network. The network gives us some physical state S. This is the SI, the input for our physical simulator. That produces the output state, SO, and that goes into the loss to be compared with the S tilde O. And so for the S tilde, we now also have, for a mini batch, j different versions to compare against. But if you look at this, it's basically this chain of evaluations, NNPL. And if we now here evaluate this with the chain rule, then we get exactly the expression I've already shown a bit earlier on the slides. Starting with the loss, we first get this vector Jacobian, vector shaped Jacobian, partial L, partial P. Then to backpropagate, we get partial P, partial SI, the input. The input was provided by the network. That means now we can compute partial SI, the output of the neural network, with respect to the weights theta of the network. And in practice, we'll actually get some scaling of this whole gradient with a learning rate, typically denoted by this eta. And then keep in mind, the gradient always points towards increasing values, increasing loss values in this case. So we need to go along the negative direction to actually decrease the loss for this linear approximation of our loss landscape at the current evaluation point. Yeah, so you'll see at the bottom here, I've already omitted the j again. In practice, this is evaluated for a whole mini batch, of course, accumulated. The contributions are, if you write it out in this L2 form, just add it up, and all of the different samples go into one combined update for the network weights theta here. Yeah. In this example I've given here, we just assumed we basically have a neural network that gives us a physical state to be provided to the solver. So we have the sequence, basically neural network, physical solver to the loss, but of course that's not all we can do. So this is just a rough overview to point out this simplification that I've made here. I'll come to more specific examples in a moment, but with the framework we've described in this course so far, because we're basically just using these Jacobian vector products, it's actually very flexible. The solver can really work in any, right, as long as the shapes, as long as basically the sizes of the inputs match, you can combine this in any fashion. Of course, it's good to stick to the ones that make sense, but it's a very flexible situation that we have here. So you can, for example, imagine switching these orders. So you could imagine in the simplest case that we actually start with our simulator. The neural network somehow evaluates the physical state, the output of the solver, and then we're computing a loss. Now we can likewise do a learning process from this chain P and NL. But keep in mind, if we now backpropagate from the loss towards theta, we actually don't need a derivative of the solver P anymore. Now the solver is more of a data provider. If we have a fast one that's in the training loop, it might still be interesting because we can maybe quickly provide randomized and flexible data to the training process. But yeah, in this case, we actually not, we don't need to differentiate through the solver. What's a bit more interesting is what I've shown before for the advection step. If we imagine we have many invocations of our solver to provide a input for the neural network, then this is how it could be written out. But in practice, more interesting is, of course, some interleaving of solver steps and neural network steps that could look a bit like what I've shown here on the bottom. You would imagine we always do a solver step, the network somehow modifies that state, another solver step, another network, and so on. until we compute a loss. Or in practice, you could, of course, also use intermediate parts here, so partially compute the loss along this chain. Long story short, basically any combination of neural network operations or solver operations and also loss operations possible here, we can compute the gradient in just the same way. Yeah, so this is really the main setup for the connection to deep learning, with the main takeaway here being, if I have a differentiable simulator, I'm very close to being very flexibly able to work with it in a learning process. And with that, now we can come to some more specific examples. So, first example that I want to give here is, we call it the solver in the loop approach. Let me explain a bit what the goal is. Here, we assume that the PDE that we're looking at has reference solutions in this blue bubble here, following these, assume it's phase-based state, will be denoted by R for reference, and we're looking at phenomena over time. Hence, we're starting at some initial condition T0, and then here with this dashed line, progress over time to some target state Tn. And right, this is our reference. That's what we like to obtain as a target. So we assume these are accurate higher order solutions. Now we can discretize the same PDE with a coarser space or a lower order method for a fast approximation, here indicated by these rougher quads on the right hand side. And if we start from the same initial condition at T0, shown here in orange with this dashed line, we probably, in most non-trivial cases, will get a very different solution over time than in this reference version on the left-hand side. So these coarse approximation will be denoted as source states in the following. And this is a very fundamental problem. Whenever we change the discretization or the order of a method, typically we have very nonlinear processes and the solutions will deviate. So even if we would have access to this reference version and kind of project it into the downsampled space on the right, it would look very different from the one with these typically accumulated numerical errors on the right hand side. And now the goal here is to employ deep learning. So have a version that uses this coarse source simulator in combination with a neural network and gets closer to this target trajectory in blue. And in the following, because you can see it as a corrector, we'd actually denote this neural network as C, given a phase-based state S and some weights theta. So this is the main setup, and yeah, you might, it's quite generic. We typically don't have closed form expressions for these numerical errors. And in this setting now, under the assumption that the solutions we're looking at are not completely arbitrary, but have some shared patterns, and the errors likewise, we will target learning them with a neural network to reduce the errors and get a more accurate solution in the end. Yeah, so this is actually a very common problem in learning approaches. You can see it as a distribution shift. So if we see it, imagine we in a very simple one-dimensional space, we might have some distribution for our source and our reference might look different. Imagine those being wave numbers or so, we might have more higher frequency content. And main point here being they're different. Now, if we have these green or aim for these green solutions, which stem from a hybrid solver using a neural network and the source one, they will inevitably also look different to the source, ideally closer to the reference, but they will be somewhere most likely in the middle with a different distribution. So the effect that our network here has is basically shifting the distribution of our solutions. And when you think about it, this is actually the input for the neural network. So if our network cannot train with these, it will most likely give a suboptimal or worst case completely wrong answer. And hence it's really important to actually have access at training time to these shifted distributions of the corrected versions. And this is exactly what we can actually achieve with these differentiable simulations by putting them into the training loop. Yeah, and also, obviously, because they just stem from the combination of the trained neural network, or the training and changing network, we cannot just pre-compute those. Let's look at what this setting gives us in practice. So first, to illustrate the simplest, the supervised setting, as mentioned before, that is the least connected one. But if we have simulations, we can pre-compute our states, the reference states with some solver, and do likewise for these source states, pair them up, and do supervised training based on this. So in the following, this T operator denotes some projection, in the easiest case, a linear averaging from the reference to the source states. Yeah, so here we now employ a network to just give us these differences. The simplest case with a supervised L2 loss is written out down here, denoting the difference between the source and the target states. And then our neural network package will directly give us the corresponding gradient for the weights theta to run this training. So this is, in a way, a very straightforward process. And this we repeat for mini batches until we've reached converged state for our neural network. One variant that is worth mentioning here is in the deep learning field what's often called a physics-informed approach. So here we likewise employ a network, but now include parts of our PDE formulation into the learning by typically taking derivatives from the neural network. And likewise compute a loss, and because the PDE is now also encoded via the neural network, we can directly get the adjoint or the corresponding gradients out of it and backpropagate. But it's, on the one hand, it's actually typically convenient, it's very easy to write out. But in these settings, typically the neural network actually gives us a uncontrollable discretization. In the computer, we have to discretize somehow, and the network somehow gives us the discretized version here. However, we have no control, and we're then actually taking derivatives of this potentially uncontrollable or difficult to control discretization. So it's actually a pretty fragile process. Takes also a while to converge. And what visually is important here, we actually do not directly use the solver here. So this is actually a very different approach to what we've discussed so far in the course. This is something that's easy to write out with deep learning, but in practice, actually not a very powerful approach and not something that I would recommend for practical problems. Rather, if you want to look at complexer settings, more demanding ones, then these differentiable simulations that we've discussed are a much more powerful approach. What we can now do here with our differentiable solver is we can actually directly unroll the evolution, the following that will be denoted by these S tilde states. So here these states are actually computed from the neural network and the applied correction for n steps. And as mentioned before, with this distribution shift, these trajectories over time now depend on the current state of our neural network. Hence they change over the course of training, and it's vital to actually see and unroll these as much as possible at training time to get a reliable answer. We can also write out the full loss function here for basically n look-ahead steps. The important bit is down there in the middle, the corrector, the neural network C, now depends on the simulated trajectories with the S tilde states. So this also indicates, again, this is not something we could just pre-compute, but this is really something we need to evaluate at training time, and keeping in mind that we assume here this P is actually one of these differentiable simulators, we can also get the gradient information for what the physics are doing with these changed states at the training time. And beyond that, it's again, just a loop here over different samples and the whole range of time steps. I think visually it's actually much more clear. We're basically unrolling the time evolution of the system we're looking at with those corrections. So we're really running the full solver for one mini batch at training time, one iteration m, for some chosen number of n steps, ideally as long as possible. Then we can start evaluating the loss. So keep in mind, in this setting, we actually, unlike the sketch before, we actually do have a loss at every step in time. We know what every one of those states should look like, but especially over time, that's where we'll actually see how the changes interact with the physics and how they actually very non-linearly influence the future evolution of the system. So now we can really make use of the differentiable solver by using computing the adjoint for the gradient with respect to the output of the neural network, which was given to the solver, and then we can keep on backpropagating this into the network to get a first update of the weights theta. But this is now actually really using the full solver, and hopefully, as discussed before, we now actually set up the computation of the derivatives in a proper manner to be done efficiently with a good discretization. So in contrast to these physics-informed losses where we don't have any control, here we can really make sure we get a good and reliable and efficiently calculated gradient for the learning process. And now here in this setting, actually we also accumulate the additional losses that come from the different time steps together with the backpropagated part. All these contributions for theta are typically additively accumulated to get one final gradient for theta. This gives us now one of these updates mentioned before. That's definitely in practice a much more complicated process, but in the end, just like discussed before, just the chain rule being applied to these nested calls of operators and functions. Now we get one gradient for our weights, which we apply with a suitable learning rate, and then we keep on repeating this process. So it definitely incurs some, when the solver is non-trivial, require a significant amount of computation for every one of the training steps, but we also get a very good direction out of it. Typically a much better one than with the other approaches. Yeah, I directly want to show a few examples. So for fluids, in a way, the simplest case to illustrate phenomena like these is unsteady wake flow. We have a cylinder here, very simple setup box with an inflow and different Reynolds numbers. Just to give you a kind of rough idea, on the top right here, you can see the source, the rough discretizations is say 4 times lower, and on the bottom, the reference. Visually, I think they clearly look very different. And if you measure the mean absolute error for the non-dimensional quantities here, we get an error of 0.14. It doesn't tell us too much for now, but if we now switch in the solver with the neural network, called solver in the loop here, SOL, then visually it's already pretty much indistinguishable. And if we measure the MAA here, it's roughly a factor of 10 lower already, so it does quite a bit better. It's a simple case, but nonetheless a good starting point. So here on the left, you can see this in motion. On the left-hand side is the coarse approximation, the source version. On the right-hand side, the reference. They all start out with the same initial conditions, and on the left, the source quickly loses all the detail of the vortex shedding, and the hybrid solver in the middle actually keeps the vortices accurate and defined. On the right is another case with a larger Reynolds number, again starting out with the same state, and then the source deviating from the target solution very strongly. So keep in mind, the middle solution, this SOL version, also uses the same source solver as on the left, but corrects it via a neural network. So I've mentioned before that it's important to actually look ahead in time to do this unrolling. And here's a graph to illustrate how important that can be in practice. So now in this graph, we're actually looking at improvements in terms of the mean absolute error. So the 0 line, that's just the source. 1 would be a perfect reproduction of the reference states, which we most likely will never achieve in practice, but we'd like to get as close as possible, of course. Now, the supervised training, mentioned before, that's denoted as NON here, that already gives some improvement, 29% better than the source. It's not bad, but then most likely this distribution shift kicks in and it stagnates. If we do this training with the solver for 4 steps, we're already quite a bit better, it's 41%. In this case, it really paid off to have 128 simulation steps of the full fluid solver being unrolled in every training iteration. In this case, that gives an improvement of 60% over the source. So in this case, we're really more than halfway towards the reference states in terms of mean absolute error. Yeah, so here it paid off by investing these computational resources. And keep in mind also, we typically assume here that we train this model once. It's definitely going to be expensive, but then hopefully we can deploy it and run it many times such that these reduced errors pay off in practice. Also, one of the key advantages of training with differentiable simulators is typically that we get better generalization. So in a way, being able to evaluate the solver and provide gradients from the simulated trajectories can provide better performance for unseen inputs, most likely because we actually train with more varied data than with a restricted set of pre-computed ones. The network really in this case learns how the source solver behaves and can adapt to different conditions, which typically gives a better generalization. So on the right here is an example from a buoyancy flow. Same setup, the source has a lower resolution, in this case also lower order solver, first order advection step instead of a second order one. And in this case, the middle hybrid version with a neural network actually typically had much better performance for new configurations of hot densities than a supervised version, for example. Yeah, we can also look at this in 3D, of course. Interestingly here, this supervised version, the NON version shown here on the left, that most likely due to the distribution shift does not give any stable answers. So this very quickly deviates and gives these weird high frequency artifacts that you can see on the left. So there's not a meaningful solution. Whereas I have it here in motion, the hybrid method sticks quite nicely to the vortex shedding features of the reference. You can see here in the motion, they don't exactly match in terms of spatial locations, but the behavior of the how confined, how large, and where these vortices form is much better than in the blurred out original source version on the left hand side. Oh yeah, 3D is also admittedly definitely much more complex case. Yeah, so for these settings, of course, one of the key questions is how does the performance do? Because we are in a purely simulated setting, the neural network replaces this reference solver, but of course we could also run it if we compute the data with it. By the way, it's important to keep in mind the reference does not need to be differentiable, only the source solver in the setup. So in our configuration here, the reference is actually a CPU-based simulator, which is fairly optimized. Took around 913 seconds for reference simulation. This hybrid solver with the neural network, around 13 to 14 seconds, which is a nice speed up. And even if you keep in mind that probably due to memory bandwidth factors, we'd still have another factor of 10 to 11 to 10, current architectures around 10, because the neural network was actually evaluated on the GPU, which still overall gives a nice speed up of 6 to 7. And I think this is by far not the end of the line. This is a first proof of concept indicating what to gain here, but I'm sure that a lot of future hardware will actually increase this gap even more. And our CPU-based solver actually was also not that bad. I think in practice you could see pretty much arbitrary speed ups from these kinds of hybrid solvers. So I hope this is a good first indicator that this combination using differentiable simulations in deep learning is actually a powerful tool. I also want to show another example where we looked at a different kind of inverse problem. So here you can imagine that we have something like a conference room or building even. Fire breaks out and we have an exhaust system that we'd like to control to, for example, transport the smoke out of the closest window as quickly as possible. So this is now a different type of problem. This is a good example of an inverse problem where we're not so interested in specific states over time, but we have one more abstract goal, the smoke being in a certain region of our computational domain at a certain time. And we don't care too much how in between, what the in-between states look like, as long as we reach this final goal as accurately as possible. So this is a different type of problem, and in this case, luckily the differentiable simulators play the same role and are crucial, but now we need actually two neural networks, one as a kind of planner that predicts what evolution to take over the course of the simulation, as shown here. We're starting with an initial state, we have some final goal in mind, given also as input to the neural network, and it then predicts in terms of velocity in this case what the intermediate states could look like. And the second network that in a way is the workhorse that does the actual actions. This is very similar to the previous error corrector. Here it's called CFE, and those two are actually jointly trained in a very similar manner to before. So as you can visually see here, it's the same setup. We're starting with states, unroll over time. In this case, we only have one final loss at the very end that's backpropagated again through the whole sequence. And here, only these CFE networks are shown. These can be trained in line with the previous error corrector, but now actually a bit orthogonal. We also have this second planning network that would also provide inputs to the CFE and that we could train jointly here together with the physics solver to solve this inverse problem. Yeah, so in our case, the room was a bit more stylized. The fire is, or the smoke from this fire is this yellow marker density, and the dark purple region is our room. At the top we have these three windows, and the exhaust system is the light blue region on the side. And the network in this case also actually learns over the same process to move the smoke into the right region and to control these exhausts in a way that we reach the desired target state. So what's actually interesting to keep in mind here is that we have a fairly large number of degrees of freedom here in this outer region of the domain, and this whole setup is similar to what you might know from reinforcement learning. So that poses an obvious question: how does it do in comparison to reinforcement learning? You could imagine running a similar, solving a similar problem with an RL approach. I'll come to that in a moment. Before that, I want to show to evaluate the quality of different solutions here. One metric that is interesting to look at is how many forces are necessary to get the smoke in the right direction. These kind of inverse problems often are relatively trivial to force if you don't do anything, and in the very last moment just force everything with a huge investment into the right state. So this is typically an undesirable solution. And these graphs show a bit what the average forces, it's a histogram of the forces per point. And as you can see here, the supervised CFE network, kind of the simplest supervised version in light gray, has a very wide kind of distribution towards the right. It needs very high forces, on average around 83 if you already train just the CFE network with this differentiable physics approach, with the gradients as discussed before, we already can lower that to around 29. And then if you train it together with this prediction network and in an end-to-end manner, then you can halve that again to roughly 14.2, so the dark blue region of forces, a significant reduction in terms of what's necessary. Yeah, so here we've now trained a neural network to solve these inverse problems. Actually, what the others in our course discussed before is you can, of course, also use classical optimization techniques. We're talking about differentiable simulations after all. Why not just use a classical joint solver to solve these kinds of problems? Now, this is also an interesting comparison, and we've looked at that. If you run the same case, or in this case, it's a slightly different setup, different target states of a fluid simulation with a regular joint method, out of the box, it actually doesn't converge. If you regularize it appropriately, you get a solution. Might look like this one. So we're getting this S-shaped trajectory. You will reach the target state quite well, but this takes more than 2 minutes and around 1,500 optimization steps. And the network actually produces very quickly, in less than a second, a much more intuitive straight trajectory. So one of the takeaway messages also for us running these tests, and which I want to share here, is the network has a big advantage here because it's actually trained with a whole collection of examples. So in practice, that really helps to prevent getting stuck in local minima, which can, for such nonlinear optimizations, very often and quickly happen. So in a way, we can train the network with a whole solution manifold of different inverse problems rather than focusing on one specific case, and that can actually lead to nice answers. Yeah, it's also worth highlighting a bit this comparison to reinforcement learning that I had before. So we're dealing with nonlinear optimizations problems here, right? So we can imagine we have an energy landscape. We're starting somewhere, this blue spot. We'd like to find some lower energy state where we typically don't in advance exactly know where it's going to be. So in practice, it's dark. We're starting at this blue point, and then we're just searching for an answer. With this supervised approach, we're basically sampling this energy landscape like before, or beforehand, to provide measurements, how we're doing, and then we're just taking a geometric average of the best solutions, or the lowest energy states that we got from these pre-computations. So typically, especially for complex problems, this averaging does not provide us with a good answer. In contrast, if we look at reinforcement learning, it's a powerful method, of course, but this is extremely costly. This typically also does not involve any knowledge about physics, and in a way, it also taps through this dark environment to explore it, and needs a large number of steps. And if you try it, it's actually also quite prone to getting stuck in local minima. So one of the key advantages of these differentiable simulations that we've discussed before is that for every step along the way, we actually get directions. So ideally, we can get to a target state in a much faster way with fewer steps. And in practice, what we found is that it's actually best, because of the nonlinear nature, to start with pre-computation to get a rough estimate and then refine these initial estimates with differentiable physics to get a really good answer. So yeah, so much for inverse problems. And then one last example that I want to discuss is reconstruction of real-world flows. So one important outlook here that I won't have much time to discuss, but which I think is very exciting and important, is to combine these differential physics approaches with means to couple with images. So with differentiable rendering, for example, or in general to close the pipeline of different steps. And we've looked at that in the context of flow reconstructions. So here you can see our setup as a sketch. At the top, you can see the different targets. So in this case, these are images. It's a filmed cloud of smoke from which we estimate an initial state, and as shown on the top left gray box, we're actually using a differentiable ray tracer here to estimate the scattering and how the image forms from this cloud of smoke. And in parallel to the observations, we have a simulation, as discussed before, that tries to estimate how the physical states evolve. And yeah, if we couple the two in line with what I discussed before over the gradients, then we can really make sure that the information flows all the way from the images, and we get a continuous signal that in the end, right, influences the physical state or the solution that's found in the neural network. So here you can see an example reconstruction from that. This is now shown from the target view. So in a way, it's relatively easy to match it well there. What's more interesting typically is how does it do from other views around. So this was an approach that actually used a single input and then an additional discriminator network to constrain the other sides. And as you can see here, the other angles also do meaningful evolutions and give overall a realistic evolution of the smoke cloud. Yeah, so much for the examples. Yeah, with that I want to come to a conclusion for my part and also for the whole course. I hope I was able to show that these differentiable simulations are a powerful tool for inverse problems in general, and especially for interesting deep learning based applications. So they're a really powerful tool to bring together deep learning and physical systems in terms of models and numerics. I showed examples from these error corrections, inverse problems, and the end-to-end combination with rendering approaches. And in a way, the main message I hope you took away here is that we really need simulators that talk to other methods, like generally you could see it optimization systems, but especially deep learning, I think, as a powerful tool for the coming years and decades, that exchange data in terms of function f, but also in terms of all higher order derivatives as necessary without any borders. So I think we should think of these simulators as something that just seamlessly interacts with optimizers or learning processes and does not artificially constrain or cut off the flow of information here. I think that's going to be especially important for all future systems and really has a huge promise for future applications of these simulations. Yeah, with that, taking a step back, our course focused on differentiable simulation for a much broader picture. So we looked at computing these derivatives that are necessary for a variety of settings, from rigid bodies, contact, all the way to fluids. We had a variety of interesting examples for robotic manipulation, some tough cases with frictional contact. I just discussed fluid simulations and the connection to deep learning. And beyond the topics that we discussed here, I think we're really just scratching the surface here in a way. It's a very active topic. There's a lot of interesting work. I think these algorithms are definitely already very useful and can be employed for very interesting applications. But nonetheless, it's a very active field. There's a lot to do. There are lots of interesting open questions, many on the theory side, right? We're dealing with complex, non-linear systems here. So understanding the theory behind it is a very active topic, but also a very interesting one, developing new algorithms, dealing with issues like robustness and efficiency. And then ultimately, I think also this goal that I've just hinted at, bridging the gap from synthetic applications to the real world, that is a very challenging step for many applications, and one where many interesting challenges exist. And with that, I'd like to thank you for joining us here, and on the behalf of also Bernhard, Stallion, and Miles, thank you for listening. Please contact us if you have questions or suggestions. With that, goodbye.